All right, welcome back. So, you ever look at a bunch of data points, just dots on a graph, and think, what's the real story here? Because, the magic isn't just in the dots themselves, right? It's in the pattern, the line that connects them. Well, today, we're going to dive into this super powerful tool that mathematicians use to find those exact patterns. It's called polynomial interpolation.
I mean, think about it, right? You get a stock price at closing time. You get a temperature reading on the hour. We know exactly what's happening at those specific moments. But what about all that time in between? What was the stock price at 10:30 a.m.? What was the temperature at half past the hour? How can we make a really good educated guess about the stuff we didn't actually measure?
And this isn't just some casual guessing game. This is a real mathematical quest. The big question is, if you give me a set of points, can I find one single, smooth curve that goes perfectly through every single one of them? That's the challenge.
Okay, to make this feel real, let's put you on the hot seat. Imagine you're at mission control, right? You're tracking a satellite. You get a ping on its location at 1 p.m., another one at 2 p.m., but then radio silence until 4 p.m. Uh-oh. You need to know where that satellite was at 2:30 to check its trajectory. So what do? You can't just connect the dots with a ruler, right? I mean, orbits aren't straight lines, they're curves.
And this is exactly where mathematicians come in. They roll up their sleeves and give us this incredible tool. The answer to our problem, the key to drawing that perfect curve through our satellite's positions, is something called an interpolating polynomial. And honestly, it's pretty much the hero of our story today.
Okay, so, deep breath. This right here is the formal textbook definition, straight from the source notes. And yeah, I know, it looks a little intense. You got your p sub n of x, your a sub 0, a whole bunch of symbols. But trust me, don't let it scare you off. The actual idea behind all this math is surprisingly simple and honestly pretty cool. Let's break it down. So here's the bottom line. Forget all those symbols for a second. An interpolating polynomial is basically a custom-built recipe. You hand it your data points, your satellite pings, your stock prices, whatever, and it cooks up a perfect, smooth curve that hits every single one of those points. It's like a master-level connect the dots.
All right, so how do we actually build this thing, this magic curve? Well, there are a few different ways to do it, but we're going to look at one of the all-time classics, a really clever method from a mathematician named Lagrange. Just think of it as our step-by-step cookbook for creating that perfect fit curve.
And boom, here's the recipe itself. Again, lots of symbols, I get it. But don't focus on the individual letters, look at the structure. See how it's just a bunch of pieces all added together? Each one of those pieces has two parts. You've got this L thing, we'll talk about that in a sec, and it's multiplied by one of the data values we already know. What we're really doing is just blending a bunch of smaller, simpler curves to make our one big, perfect curve.
See, it's really just a four-step process. Super simple. Step 1, you list out all the points you know, your dots. Step 2, for every single dot you build one of these special basis polynomials. And here's the trick, the secret sauce. Each one of these is built to be 1 at its own point and 0 at all the other points. It's genius. Step 3, you take each of those special polynomials and multiply it by its data value. And step 4, you just add the whole shebang together. That's it, you've got your curve.
And check this out, here it is in action, pulled right from the source material. Over on the left, you can see the math for building those 3 individual basis polynomials. They're called L0, L1, and L2 here. Then on the right, you see them being multiplied by the data values and then just add it up. And the final answer? That's it. That's the one polynomial that will perfectly slice through every single one of our original dots. Pretty cool, right? It actually works.
Okay, so this is awesome. We have this super powerful method we can draw a perfect curve through any points we have. But, and this is a big but, this leads to a really important question. Just because our curve is perfect on the dots, does that mean it's a crystal ball for everything happening between the dots?
This is where we have to put our thinking caps on. That polynomial, it's our best mathematical guess, right? It's based only on the info we gave it. But think back to our satellite. What if it wobbled a little bit between that 2 p.m. and 4 p.m. ping? Our nice, smooth curve would have no idea. So when we use it to predict the location at 2:30, just how confident can we really be in that answer?
And of course, mathematicians have thought of this. They've got a formula for everything, right? So this right here is the formula for what's called the interpolation error. Basically, it gives us a way to figure out the potential gap between what our polynomial predicts and what the real true value might be. Now, you don't need to memorize this thing. The big takeaway is just knowing that mathematicians have a way to measure the uncertainty.
So here's what you really need to remember from all this. Interpolation? It's an amazing approximation, but it's not a magic 8-ball. Your predictions are going to be the most reliable when you're staying close to the data points you already have. The further you stray from your known territory, the bigger that potential error gets. So that guess for our satellite at 2:30 p.m., probably pretty solid. But trying to use the same data to guess where it was at 8 p.m., yeah, that's way, way riskier.
Okay, so we get the power and we get the catch, the nuance. So why does any of this matter? Let's talk about the real world, because this isn't just some abstract math problem. This is a technique that is literally building the world all around us in ways you probably don't even see.
Ever wonder how a character in a video game moves so smoothly? Animators don't draw every single frame. They set the key poses, the dots, and a computer uses interpolation to create all the fluid motion in between. That smooth curve on an airplane wing? Designed with interpolation. Data scientists have missing numbers in a spreadsheet. They use interpolation to fill in the gaps intelligently. I'm telling you, from predicting the weather to modeling stock prices, this idea of connecting the dots is absolutely everywhere.
In this quote, I think just hits the nail on the head. The essence of mathematics is not to make simple things complicated, but to make complicated things simple. That's exactly what we just did, right? We looked at these kind of scary-looking formulas, but we realized their whole purpose was to solve a really simple, intuitive problem. How do we connect the dots? It's just a perfect example of how math can take something that feels complicated and make it simple and incredibly powerful.
So that leaves us with one last thing to think about. We've got this amazing power, right? We can take a few scattered dots and find the pattern, create a beautiful, smooth curve. But we also saw that it's not a perfect window into reality. It's a model. And that leads to the real big picture question. How do we know when our model is actually reflecting the real world, and when is it just a pretty curve telling us a story we want to hear? Something to think about. Thanks so much for tuning in.